Is it podcast time again?
It is podcast time. Welcome to Ask Erin, Dear Beth, with your hosts, Erin.
And Beth.
Oh my gosh. So good to see you, Beth. Thanks for joining me.
Pleasure as always.
Okay, well, today I wanted to, so recently talked about cell profiler features that we use in the cell painting assay. So got
Two new things to link to.
Yeah, lots of links in the show notes in case you don't know what I'm talking about. But the idea being that recently I was talking about morphological features. So we're doing morphological profiling is pretty, standard in our lab where we are making measurements of cells as sort of an omics way of describing cells based on their morphology. And cell painting assay being the field standard in our field right now. And I talked about the features that we get out when using CellProfiler to make measurements in the cell painting assay, and talked about how they're interpretable, how a biologist might be able to help you understand what each of those measurements are. And I kind of contrasted that to a lot of deep learning ways of profiling cell morphology. You're getting out totally uninterpretable features. Feature name is like feature 732. You're like, I don't know what that's describing.
Yeah. What is feature 732?
Who knows? But I wanted to show off a little bit of work that helped a tiny bit with that actually uses deep learning and has some of the strengths of deep learning, but also you still get interpretable features. So as we're going to do
that sounds fancy. I
yeah,
like it.
tiny little journal club here. So this was a project that I sort of was looped in on the end, led by Asaf Zaritsky and his lab. And I helped sort of provide some of the biology intuition in the end. But I think it's a really interesting example of using deep learning, but still having biological interpretability of features that I wanted to highlight. So
we don't just want to be like, ew, deep learning. Deep learning's, but like, no, deep learning is good. Like,
yeah. I mean, there are many wonderful things that it brings us. So here in this graphical abstract, I'm just going to start by just talking through the graphical abstract. So we've got the cell painting assay. So this is actually this paper is using published cell painting data sets, all pulled from the cell painting gallery. I'll drop that in show notes as well. And so this is historical data that Asif's team worked to create this new way of taking these original historical data sets and using deep learning to improve the strength of the features so we can get more hits called, more biological discovery out of these existing data sets. So we started with cell painting. This is just a setup of a cell painting plate if we think we're zooming in the corner, although one should never line up their control wells all in a row. This was just my quick way of illustrating it. But, side note, this is not actually how the plates are arranged in real life. But if we think of...
Usually, sometimes they are.
Yeah, this is not how they should be arranged in real life. So we have these control wells and, as these white, and then treatment. If we think of, we've added different drugs to each well, and some of them are going to cause lots of morphological changes, and some of them will cause less. And so those are, here more similar to the controls. So if we then think of this in terms of feature extraction, so these classic features are cell profiler features. So they all, go back to, well, link in the show notes about cell profiler features and what those look like, but they tell you which compartment we made the measurement in, what kind of measurement it is, what image we use to make those measurements. So we know lots and lots of information about what each of those features actually is. So this is our starting point. So then the cool thing that Asif's group did was they trained a model, deep learning model here, using only the control wells. So generally, when you're talking about training a deep learning model, and we also have an episode sort of about machine learning and some intuition about that that Beth led before. So I'll drop that in show notes too, because that's some helpful, helpful conceptual background. I know we've got
Mhm.
um,
So many episodes.
so many episodes. So normally when you're training a deep learning, any sort of machine learning model, whether it's classical machine learning or deep learning, you want to include data that is representative of all of the data that your model will be encountering. Uh, but here, they did a very interesting thing where they trained this in distribution model, so only on the control wells. So this model is trained to take in CellProfiler features and spit out the same CellProfiler features, basically. So lots of simplification of what I'm doing here to describe this.
Mhm.
Go read the paper if you want the more technical details, but I'm simplifying things a lot. So this model takes in features and spits them right back out again. And the key here being it is trained only on control wells. So then what we have, we can math the reconstruction and say how different is this reconstruction from the original actual features. And we can see that on control wells, it does a pretty good job. Mostly, we did a good job of training a model here where I can, put it in, get the thing in, and get out what I want. So we have very little signal in our reconstruction here. So the reconstruction being how bad did it do at the output. So then what's cool is they took that same in distribution model that is only trained on control wells and said, okay, if I put in features from treated wells, what do I get out? And you can see then that like some treatment conditions, it does a totally fine job of it had enough information trained on just the controls that it is able to do a good job of reconstructing. But for many treatments, it's saying for this treatment here, I didn't actually learn enough information when I was trained on just control wells to come up with something accurate. So I have a bunch of error here in my reconstruction. So this is the error, the amount of error. So that is saying that this treatment here is quite different from the control wells because it was not included, like it's too far out of the distribution of what this model was trained on to be able to do a good job of reconstructing it. It is too different from how this model was trained.
And
So,
I love this approach because it takes something that is a limitation of deep learning models, which is they tend to only be good at exactly what they've seen, and flips it around and says, okay, well, what we actually want to know is what's different. So let's take a weakness and make it a strength. That's why I love this approach.
yeah, yeah, super cool. Super cool. So then, we can then plot, if we look at the amount of error in control wells, right, in terms of, this is like a density here, saying like, okay, there is going to be some level in reconstruction because it is not perfect. But in our treated wells, we're getting a lot more error at reconstructing. And so then you can set a threshold and say, okay, anything like a 95% confidence limit here, where we say like, okay, if it is um, worse, more poorly reconstructed than 95% of the control wells, we can call it a hit and say that we can trust this phenotype. It is strong enough that we can distinguish it from our control population and call hits. And so they then did that for 4 different data sets. Again, historical CellProfiler data sets. Um, and we're able to show that the anomaly profiles are more reproducible than CellProfiler profiles. So able to call more hits. So better separate, better able to say like this is a real phenotype that I can really measure and distinguish it from a control population. And then they actually looked at a biological task of figuring out the mechanism of action of a drug. So saying we know, we have some known information about the drugs that were the treatment conditions here. Can I classify them, knowing, using this biology I know? And the anomaly profiles did better. Batch effects are a major problem in the cell painting assay, and it reduced the amount of batch effects. And then the cool thing, again, that I'm highlighting here is that we retained biologically interpretable features. So the features we get out, right? So I can say, like, I had this reconstruction. I failed to reconstruct the intensity level in the ER, for example. Like that was very perturbed. So these features that we get out in these, in these anomaly profiles are actually the same feature names as the CellProfiler features. So we have a level of interpretability, and we can use that to do some biological discovery um, in a way that we can't if it's feature number 273, right? And then finally, for the sake of time, I'm not going to dive into this either, but you can actually use this to identify alterations in relationships between features. So, one thing that is a blessing and a curse in the cell painting assay, like we start with thousands of features, but lots of them are very highly correlated with each other. There's lots of, so we do some level of feature selection to drop down from thousands to hundreds of features when we're like to look at the profiles that we're using for biological discovery. But there's still a lot of very tight correlations between features, even after our sort of standard feature selection. And you can, in this situation, these reconstruction errors can actually give you information about broken relationships between features, which can then lead to really cool discovery where, like, normally, if you have more neighbors, you have more roundness, right? Because cells are packed in closer together and there's just not room for them to spread out. But, we show an example where this broken relationship between number of neighbors and roundness might actually, can suggest here's again a biologist's interpretation of what this could be, where the cells are sort of always the same amount of round, no matter how much space you give them to spread out. And so that is a change in biology. Something interesting is going on there. And go read the paper if you want to deep dive into more. But yeah, this was a really fun project to be looped in on, and a really fun way to, again, like lots of strengths here. We can see the strengths of using this deep learning, but also retaining the benefit of biological interpretability of these output features so that you can drop a naive biologist in at the end of the project and they can give you like actual biological insight because we have these feature names that still exist.
An excellent biologist. Not that's the adjective I would use.
Thank you. Thank you. Yeah. And again, thanks to Asif for looping me in on this project. And thanks to y'all for listening.
Yeah, go read the paper. It'll be in the notes. It's a super cool approach. I love it. I'm super excited that you guys did this.
Yes. Yeah. Thanks.
All right. Talk to you later.
Bye.